Go.
Well, now let's talk about the geologic history of the Reno area. There have been a lot of really exciting events that have taken place in Nevada over the past several hundred million years, I should say. But Reno itself, the rocks around our basin, our small little basin called the Truckee Meadows, are relatively young in age in the grand scheme of things. You think about the Earth being 4.5 billion years old. These rocks around Reno, the oldest ones that we typically find, are 248 million years old and younger. These rocks coincide with the Mesozoic era. There are older rocks in Nevada, of course, but the fact is that these older rocks simply aren't exposed in our part of Nevada. So beginning about 540 million years ago, we had this area of Nevada, western Nevada, was under a deep marine environment. So we were underwater here. There were no Sierra Nevada mountains to our west, no basin and range to our east. It was just a big marine environment. And so rocks that were deposited here were, your typical sedimentary rocks that you would see in a marine environment, like limestone, which we talked about earlier. So starting about 248 million years ago, which was the start of that Mesozoic era, as I mentioned earlier, we transitioned to more of a shallow ocean environment from that deep marine environment that I mentioned. During that time, our plate margin that was previously in eastern Nevada started migrating to the west and was now located just over the Nevada-California state line where we see it today. So this depositional environment allowed for more shallow marine sediments to form, and in this time frame, which also coincides with the age of dinosaurs, so our Jurassic, Triassic, and Cretaceous, we also find fossils in present-day central Nevada from ichthyosaurs and other marine life. So you can find those today if you head out west to places like Berlin Ichthyosaur State Park. So between 248 million years ago and 144 million years ago, so this would have been the early part of the Mesozoic era, our area started experiencing a subduction zone. So this is where we have two tectonic plates coming together. And in this case of a subduction zone, we have one plate that is the continental plate. So this would have been the North American plate, which our continental plates are composed primarily of granitic rocks. They tend to be thicker, but they are less dense. Our oceanic plates are composed of basaltic rocks. These plates tend to be thinner, but are much less dense. So when these two plates come together and collide, the oceanic plate being more dense, subducts underneath the North American continental plate. So this started happening between 248 and 144 million years ago. This also caused the subducting rock from that oceanic plate to turn to magma. Well, what happens when rock turns to magma and gets hot is it rises. So as those rocks melted and turned into magma, we had extensive amounts of volcanic activity occurring in this area. Think of it as present-day Cascade Range type volcanism. So today we have the Juan de Fuca plate, an oceanic plate, subducting underneath the North American plate, or continental plate, just north of here. Actually starting the Cascade Range, our farthest south volcano in the Cascade Range is Mount Lassen, which is actually just located not too far north of us. That Cascade volcanic arc goes all the way up towards Canada. So that's what happens with our subduction zone. So rewind to about 144 million years or so ago, and this is what was happening here as well. So during this time of subduction, where we had all of the active volcanic activity going on, we also had some intrusive igneous rocks forming. These were rocks that would later become the Sierra Nevada batholith. So a batholith is an area, a group of intrusive igneous rocks that extends over a large area. Our Sierra Nevada is primarily composed of these granitic rocks, and that's why you hear geologists referring to the Sierra Nevada batholith. So this formation of the batholith occurred in the latter half of the Mesozoic, most likely during the Cenozoic time period, which was about 144 to 65 million years ago. These rocks, as I mentioned earlier, cooled very slowly underground, and over time the rocks that were deposited above them, so those volcanic rocks associated with that subduction type volcanism, eroded away, and uplift and erosion occurred, where we now are able to see those Cretaceous granitic rocks of the Sierra Nevada. So until fairly recently, geologic speaking of course, these rocks of the Sierra Nevada batholith were all buried underneath those volcanic rocks associated with that subduction. It wasn't until about 15 or so million years ago that we started to see these rocks being uplifted through different tectonic processes that occurred in this area. So around that time, a little bit before that time, this area started transitioning from a period of active subduction, where the oceanic plate was subducting underneath the North American plate, to a more transformed plate boundary. So that plate boundary changed from a subduction zone to what we see today as the current boundary between the North American plate and the Pacific plate, being that San Andreas Fault, which is a strike-slip boundary. So in this area we have one plate, the Pacific plate, moving north relative to the North American plate. So this had a few implications for Nevada during that time. Again, around 15 million years ago, that's when our subduction kind of tapered off and we transitioned to that more of an extensional environment for this area. So that extensional environment basically means that we have our crust is now being pulled apart. I'm going to check out these fault block diagrams that I have right here. So imagine this as the crust, and I'm going to apply some forces pulling the crust apart, and now we see how one of these blocks drops down relative to the other. This is what's happening in Nevada today. As this was happening, we also had a period of younger volcanism occurring in this area. Many of the rocks we see around Reno are these rocks that were from these volcanoes associated with our extensional environment. So when our extensional environment began, the crust began to thin out, pulling apart, and magma and hot rock deep below the surface worked its way up through fissures and cracks in the crust. As a result, this formed many volcanoes around the area, depositing extensive lava flows that we can still see in this area today. So the Sierra Nevadas, as we know them today, were probably only uplifted around 6 million years ago, which sounds like a long time, but in the geologic history of things, it really is quite recent. We can pinpoint this date down because of fossil evidence that we find in parts of Nevada today. The fossils that we find tell us that during that time we had a much more wet environment, probably more like things were in present-day Auburn, California. More water, so we were able to see maple leaf fossils and things like that. When the Sierra Nevada were in place, these are a high mountain range, so they cause what we call a rain shadow, pretty much blocking a lot of the moisture that we get coming off of the Pacific, making Nevada one of the driest states in the United States. So even more recently than that, we can talk a little bit about glaciation in the Sierra Nevada. So here at the Visitor Center, we're standing on what we call a glacial outwash plain. This was debris that came out of the canyons, out of Jones Creek Canyon and further south out of Galena Canyon, associated with glacial activity. In the Galena Creek Canyon, there are areas that we can even see that geologists have mapped as glacial moraines. If we were to travel up this canyon a little ways farther, we would also be able to see some glacial moraines of the Tioga and Tahoe age, which is a late Pleistocene in age.